Okay, so I'm really excited everybody's here. I haven't sort of talked to a lot of people yet because my head's been full of trying to make sure everything's organized and this talk, and there hasn't been a lot of room, sort of cognitive space for anything else so far. But in an hour and a half, I will have this talk done, and then half my brain will be free again, I guess. So I'll have figured most things out. So I do apologize. There's a couple of things about this talk. So I gave this talk about a month ago, but I had 3 hours to give it then. So I'm trying to give it in an hour and a half, or perhaps even less, so we can get over to lunch in time. We have to go. I think it finishes at 1, so we have to. No, 1:30. So we need to go pretty sharpish after I finish to lunch. So there's that, plus the conference, so conference organizing, so I think I may be referring to my notes just to make sure I'm not missing anything a bit more than I usually would. Okay, so please forgive that. So what I aim to do here is really an overview of string theory, and in particular with a focus on the relationship between matter and geometry in string theory. So that's an awful lot of ground to cover, like a semester or two of graduate physics courses in an hour and a half. But in a way that's okay, because there's a lot of details along the way there, and what I really want to sort of give to people is the sort of conceptual story that's behind all the details. Because in general, there's a lot of familiar things that are involved there. What it relies on is a lot of things in a lot of ideas and concepts from quantum field theory. So the talk has sort of multiple audiences. For people who already know some quantum field theory, the idea is to just point out what the salient ideas are, so that when you study string theory, you can see it's really a pretty familiar kind of system with some sort of particular results. I guess to be even more ambitious, I'm going to try and explain quantum field theory as well, so that people who don't know that can understand some of the basic ideas too. And I also have him. So there may be more or fewer parts of this talk that are really speaking to you individually. By the end, I do want to get to the point where you understand the status of general relativity, gravity, geometry in string theory, because that will be relevant to some of the groups that I'm going to be talking to this week. All right, so I guess the best thing would be to get started, and you see it there. So 3 parts to the talk. We're going to talk about the particle concept within string theory first. Then we're going to talk about the important idea of background fields in string theory. What does it mean? How should we understand it when strings are propagating in a classical background that seems to be specified in the dynamics? And from that, how do we get general relativity out of string theory? Good. So part 1 with the particle picture. And to start here, and to emphasize that although there's a lot of very kind of interesting and deep mathematics in string theory, there's a certain strand in string theory, a certain strand in which it involves some very basic ideas. We'll start with talking about a classical relativistic string. And although it's not a system that gets studied in I think undergraduate physics, it's actually a very nice and not too hard kind of system to study. So I brought a model of a string right here. I used to have a little longer one, but I lost it in Brazil, but this one works almost as well. So this behaves almost exactly like a string. So it's a spring that's for a garage door opener, and if you think about, let's see if I can throw it up and not injure anyone. Yeah, that worked pretty well. So what we're interested in is the motion of a thing like this. And of course what you see is, to describe its motion, it has a position at any time, it has a velocity, it's moving up and down, and you also see, eventually, it's the vibrations that it has. The slightly longer one, you'll see it always has like two nodes where it's vibrating about, so I have sort of two waves on here. The slightly longer one, if I really did it hard, I could get more nodes in it as well. But you can imagine that it could have other vibrational modes also. I mean, it has that vibrational mode as well, where it doesn't vibrate at all, of course. Okay, so what we want to do in string theory, and we're just going to do the classical case first, is sort of figure out what the physics for such an object would look like. The picture down the line is, if this was really small, and I didn't have a very big sort of microscope, I wouldn't notice that it was a string, an extended object. I would just see sort of a point particle. And what we see in terms of the different vibrational modes, because we see it as a string, then are going to look like internal degrees of freedom of this particle, and in particular are going to lead to different masses and spin states of the particle, of this stringy particle, as it appears to me. And so I'm going to be able to identify what appear to us as particles as in fact just different strings in different, strings that are otherwise the same but in different internal states. So what appear to us to be fixed intrinsic particle properties are really dynamical internal properties of strings. Okay, so you've probably heard that before, but that's the point I want to kind of work out here. Let's see what we've got here. So let's just think about setting up the formalism. So the general way to think about formalism. So this is an open string. So I'm going to picture it as something like this. So imagine it in space and time. And I've got my string kind of propagating, and I guess I should draw some, make it look like it's wiggling a little bit as it goes along here. Right, it's moving through space and time. It's going to be internal coordinates. It's a one-dimensional object in space, a two-dimensional space-time object. And so internal coordinates on the string, sigma and tau. I could also have a closed string, and same sort of deal here. There's different conventions about what these endpoints are. I think I've kind of taken all the constants out of my equations, but if there's any constants left in, I put 0 and pi at either end. Okay, we're going to really mostly be focusing on the open string for our discussions, although results about the closed string will also be important. So what I've drawn here is the world sheet for the string, and these are the space-time coordinates, and a trajectory. So it's cool. I'm going to use big X's for the space-time coordinates. So big X0 is the time, and this could be X1. We're going to assume there's d space dimensions. So this space-time has overall d+1 dimensions. I'm not going to talk about that too much, but you probably know one of the features of string theory is that this is not 4, d is not 3 generally, it can't be 3. So that's why we have that. I'm going to call this as a background space-time. It's the space-time I specify in which the strings are propagating. The later part of the talk we'll be talking about what it means, what the status of this background actually is. We will come back to that in a second. So to give a trajectory, the trajectory then is going to be a map from this the world sheet W, this M can be the space-time, is a map from points of the world sheet into the space-time. I need to tell you for each point of the string where it is in space-time. That's a specification of the trajectory. And so in the fundamental kind of degree of freedom for the string is x mu as a function of so that's the space-time coordinate as a function of the world sheet coordinates. That's how you're going to describe the motion of the string. But there are two ways to think about this. There's the world sheet point of view, the space-time point of view first, which is the one I've been assuming, where I've been thinking about the world sheet this thing has, and for each point on here telling you where it is in space via this function. So that's the space-time point of view, thinking about how to embed this world sheet into the space-time. I mean the background space-time. But for the same mathematics, there's also the world sheet point of view, where you kind of think of the world sheet as itself a two-dimensional space-time with these degrees of freedom living on it. Right, so there's a particular point, sigma tau. That's the point it's located. From the point of view of the world sheet, what it looks like is that I have d+1 sort of fields living on the world sheet. Okay? In some sense, it looks like a d+1 vector field, tangent vector field to the world sheet, but a set of d+1 fields at each point on the world sheet. And we'll kind of flip back and forth between these 2 points of view. In the space-time, it's about where the string is located. From the world sheet point of view, well, these x mu's look like fields. And this point of view is pretty important for seeing how to apply the techniques and ideas of quantum field theory to string theory. But it's just the same as describing it this way, really. Okay. Let us make, for now, what I'm going to talk about in part one, part one there, I'm going to assume it's relativistic, and there's no forces, not even there's no forces and no gravity acting. So it's not quite like we have here, where this is moving in a gravitational field. It's going to be force-free. So we're going to assume a Minkowski metric. Okay, and we'll sort of elaborate from there later on. Okay. So let's think about how the physics is going to go. So if it's relativistic, you kind of expect that there should be, we're going to look from the world sheet point of view, kind of expect a relativistic wave equation for these, for this field that's living on the world sheet, and that's what we're going to go with. And in that case, you expect the solution. That doesn't work. Okay. You expect there to be this kind of solution that you expect is going to be a wave equation, and it's like I said. There's sort of an initial position, and then there's a term telling you about the motion of the center of mass, and then there's some sum of oscillations. So these are the different modes, vibrational modes of this, correspond to the different vibrational modes of the string. They're vibrating in time, they're vibrating in space, and then these are the amplitudes of the different modes that you see here. So, I only had like the second mode, so everything, these are all going to be 0 for that picture, except with the 2 vibrations. So this is a kind of Fourier expansion for the vibrations, right? The fact that there are cosines here comes from the fact that we have Neumann boundary conditions, which are giving us momentum conservation at the edges here. For those in the know, later, in later developments in string theory, you see that there could be Dirichlet boundary conditions that actually fix these edges. For the closed string, of course, we don't have sort of edge boundary conditions. There's going to be periodic boundary conditions. And I think that's probably something Friday will talk about Thursday. Okay, but this is pretty, still kind of. This should all be is pretty basic kind of classical physics. I don't know what your physics degree was like, but I spent sort of 3 years solving different kinds of wave equations, and so that's all that's going on here. So that's what things look like. There is one way in which my spring is disanalogous to the string. Right, no vibrations right now, but it still has a finite length. But you can sort of see if all these amplitudes are 0, the string is contracted to a point. The only reason it has length is because of how it's vibrating. Otherwise, it's okay. So you can sort of see those internal degrees of freedom that are going to look like different particles are all kind of encoded into these amplitudes here. It's the different values of those that are encoding the different internal degrees of freedom of the string, because they're telling you how it's vibrating, the different modes of vibration. And so, just to be clear, and for anyone who's not sort of familiar with the terminology, this is a sum over mode, orbital modes. Each n corresponds to a different mode, and you can see the n determines the wavelength of the vibration. Because it determines the period of the cosine here. Okay. One other thing about the closed string, things work the same, except don't have the boundary conditions, you just have periodic conditions, and as a result, it looks the same, except it looks like kind of like two open strings. You have vibrations going to the left and vibrations going to the right. So you'll see, you get sort of more things that are possible with the closed string. They're sort of more interesting for that reason. Okay. So it's useful to switch to a sort of action point of view to describe things. So I'm just going to remind you about Hamilton's principle, all classical here. The physically possible trajectory between any given initial and final states is the one with the least value of the action. I bring this up because there's going to be an echo of this later on. For the string, the first action people explored was a rather beautiful one, the Nabu-Goto action, which says that well, the value of the action for any path is really some constant t times the worldsheet spacetime area. So you kind of integrate some infinitesimal worldsheet distances over the string. So putting these two things, that interpretation of the action together with Hamilton's principle, tells you that the law for the relativistic string that I was just talking about is, given initial and final states, the path it'll follow is the one with the least area. So that's a really kind of nice geometric interpretation of what's going on. Turns out this isn't a very useful action when you want to do quantum mechanics, and we'll look at a different equivalent action. But yeah, this is a nice geometric interpretation for the classical string. And indeed, it gives you when you minimize this, when you apply the Euler-Lagrange equations to that action, you get the relativistic wave equation out. And indeed, what I've written up there is the solution. It is the trajectory that minimizes this action. So all these pieces hang together. Okay. So one of the things that T is has the units of a constant tension. I won't explain that, but it actually amounts to a tension in the string. And it's worth noting, because the string is relativistic, it's not obeying Hooke's law, where the tension depends on how much the string is stretched. That doesn't really make any sense relativistically, because the length of the string is dependent on the frame, so it's hard to have a Hooke's law version. So the string has constant tension. That's what that T is. Okay, and as I said, if we let the T be really high, so that the string is really small compared to our measurement scales, it's going to appear as a particle. So let's think that through. So we're imagining a stringy classical particle. Now, if it's a particle, the theory is relativistic. That particle is going to have to obey the standard mass-energy relationship. So, if m squared is the rest mass in an arbitrary frame, that splits up into energy and 3 momentum, and so this is just the standard relativistic mass-energy relation. That's got to have to be satisfied because it's a particle. It looks, if it's behaving like a particle, and the theory is relativistic. This term here, is the 4 momentum squared, which comes from this second term up here. Ignore the first term. We could just pick coordinates to set that to 0. So this quantity here, the mass energy, is related to this velocity, this d+1 velocity term. Will give us this. It also turns out, because of the symmetries and of the theory, that there are non-trivial constraints between this term and these terms, the Virasoro constraints, the gauge constraints, which relate. So this is related. The 4 momentum squared is related to this term in the solution, and by the constraints, that's related to the other terms, the modes in the solution, and this there's going to be several parts where I just have to pull something out of the hat for you, and you can go look at one of the textbooks and they'll show this for you. This is related to these in such a way then that the 4 momentums, d+1 momentum squared, is equal to this quantity. As I said, it's a relativistic particle, so the 4 momentum, d+1 momentum squared must be equal to the mass squared. So the combination of thinking of the string as a particle and the constraints of the system give you a formula for the mass squared in terms of the amplitudes of the modes. It just looks like this. Okay, so indeed, the way it's vibrating, the particle is going to, depending on how it's vibrating, it's going to look like it has this mass or that mass, different kinds of masses. Not really too surprising from a relativistic point of view. It has this energy from the vibrations, and of course, when you just look at it as a particle, all right, that looks like the rest mass of a particle, if you forget that that's an internal degree of freedom. So it's exactly what should be happening intuitively, does drop out mathematically. Okay. For the closed string, as I said, you're going to get left vibrations and right vibrations. So there's going to be another term you'd get a term like this for vibrations going left, and a term like this for vibrations going right. And what you were, okay. Of course, that's all classical, and these mode amplitudes can take on any values. That gives you a sort of continuous mass spectrum. The world's quantum mechanical, particles come in with discrete mass spectra, so that's what we want to turn to next. Okay, so there's quite a lot there, but that's the basic classical picture. Any questions before I go on to talk about this from a quantum point of view? I really haven't said anything other than, you've just got this classical thing bouncing around, and this is just developing the kind of formalism you'd expect. Yeah.
Yeah, I have a question about the non-polar reaction. It only works for closed strings, or is for all strings?
The open string as well, yeah.
For open string.
Yeah.
But because maybe I'm missing what area is minimizing.
So it's a space-time area. It's not just the space area. So you kind of take the construct an infinitesimal kind of Wiltshire area and integrate that out. So it's a funny kind of area, but that's what it's to. Yeah. Okay. So we have to apply quantum field theory to this string. So first I'm just going to spend 5 minutes either reminding or teaching you quantum field theory. Again, just the very basic sort of idea that goes on here. So, okay, we're going to start with classical field, and Fourier expand the classical field in modes, pretty much as we just did. Okay, so there's just a do it in complex modes, because I have e to the I terms. You plug that into the relativistic wave equation, so thinking about a free field, you'll find that the different modes satisfy a simple harmonic oscillator equation. So you can think of the classical field as this sum of harmonic oscillators. I've got a sum to keep things, I've sort of put periodic boundary conditions, so that's why there's a sum, so I don't have to integrate and I don't have to worry about measures or anything. I'm just keeping everything as simple as possible here. Talking of things as simple as possible, obviously I'm setting the speed of light c equal to 1 when I write this. I'm going to set h bar equal to 1, and there may be points where I set pi and 2 pi equal to 1 and things like that, okay? Because it's really the form of the equation, so you can sort of see, you have to fill in a lot of details to really be comfortable, but just the point is to go through the conceptual development. Okay, well, since the classical field is a sum of simple harmonic oscillators, we can understand the quantum field by thinking about how to quantize each of the individual simple harmonic oscillators. And Dave already kind of assumed that you knew this, so I won't spend much time about it. So I'm thinking about this classical equation. Forget about the particular modes, because I'm just going to pick an arbitrary simple harmonic oscillator. You promote the amplitude to an operator and the complex conjugate of the amplitude from the other term to the emission conjugate, and then you impose, generally if this is actually vibrating, you've got XP commutation relations, and they will entail this a commutation relation of this form between the two amplitude operators, and so again, an elementary sort of system that you study in quantum mechanics. What you find is, to represent this algebra, there's going to be a series of states with a lowest state but no highest state, labeled with n, such that the daggered operator, one of the operators, which we'll say this is the one with the daggered operator, takes you up the series from level m to level m plus 1, so that's the raising or creation operator, and the other operator, the undaggered one, takes you down. So that's the annihilation or lowering operator. Obviously there's some normalization constants in there. And the other thing to remember is this combination of operators, the A dagger A or alpha dagger alpha, is the number operator. It will tell you if you hit it on one of these states, the eigenvalue you get back is the level of the state. So that's the number operator. So that's a particularly important one. Okay. So there's a sense in which this idea, which is a sort of pretty elementary idea from classical physics, and this idea, which is an elementary idea from quantum mechanics gets you to quantum field theory, because what do I need for a general quantum state? I've got a load of, I'm going to quantize each one of these modes. So for each one, I'm going to get a spectrum, like a set of states like this. So a general state is going to require me, for each value of n, to tell me which of these levels that simple harmonic oscillator is excited to. Or at least that's going to be a basis of states, rather. So the subscript here again applies to the n. So for each of the modes in this expansion, I've now quantized it, so I know it's going to have a basis of states that look like this. And so a basis of states is going to specify for each of the modes which level of excitation it's in. Okay. So let's think about those states in particular. So each one of the modes is a particular wavelength, so it corresponds to a particular momentum. So you could think of a state like this as saying that there are, m1's quantum particles in the first mode, the momentum corresponding to the first mode, m2 in the with the momentum corresponding to the second mode, and so on. This is a specification of a collection of quantum particles, each with different possible quantum momenta, and a specification of how many of quantum particles have each of the possible momenta. Right? And the m's tell you that. What makes this kind of more interesting is, right, that's just a basis. So the principle of superposition in quantum mechanics says that I can superpose such states. I can take a particle with, I can take you can take the state with, say, one particle in the first excited or in the lowest mode, and two particles in the lowest mode, and take their superposition. And then, well, on a standard understanding of quantum mechanics, it's then sort of indeterminate whether there's one particle or two particles. And so really, when you bring this principle of superposition to this picture, you shouldn't think of these as particles because of superposition, and of course because I can create, using these operators, give you a system where you can create another particle in a particular momentum state, or annihilate a particle in a momentum state. Because you can change the number of particles, and because you have states with indefinite numbers of particles, these really, it's better not to think of these as quantum particles, but as quanta, this kind of new thing that don't have to come in definite numbers, you can create and annihilate them. Unlike ordinary quantum mechanics or multi-particle quantum mechanics, before you have the fields, you have a single particle or two particles, and that's a constant of the system. I would say use the term quantum particles to talk about that kind of system, but when you have fields and this other possibility, quantum. And that vocabulary is going to be useful for understanding what's happening with the string, the state of the string theory. Okay. I didn't really talk about strings much, but there's my field, and we started by Fourier transforming the classical field, and we sort of already have that in our solution for the strings, and we're going to get exactly the same thing. These are going to be simple harmonic oscillator modes, and we're going to get, we're going to get a commutation relation when we promote these to operators in just this way. We are again going to get a commutation relation that makes these raising and lowering operators for modes on the string. Okay. Just to sort of step back classically, the string's wobbling all over the place, but the state I want to describe, I'm going to describe by adding up with the right amplitude a collection of different waves that are on the string. Okay. That's going to be quantized, so now I have quantized levels of the different amplitudes of the different modes of string vibrations. Okay. Comment. So I've just explained string theory, quantum field theory in this way, in terms of simple harmonic oscillators and what's known as the Fock representation, the Fock picture. I think conceptually that's going to be useful for what I want to say about string theory. I don't think it's the right way to think about quantum field theory, however, because it sort of assumes that quantum fields are coming from quantizing classical fields, and that's a sort of unfortunate way to think about quantum mechanics. I mean, the world is really quantum first, and then the question is, why does it look classical? It's not, how does the classical world change to a quantum world? But it's useful for this very sort of short presentation, and you should go read, I think, Weinberg's quantum field theory text or something if you really want a good way to think about, start thinking about quantum fields, where you start with particles, in fact, quantum particles, and you see the necessity for quantum fields interacting. Okay. So, field theory, and we see the string. Again, we're sort of taking the worldsheet point of view here. This is a field living on the string, and it expands in just the way we were looking at in general. All we want to look at really, I hope, is the mass formula. So I gave that to you classically. It's going to be on quantization, the amplitude, right? This was the formula I gave you earlier for the mass squared. On quantization, these are going to be promoted to operators. We have an issue here, though. Classically, it doesn't matter which way round I write these two amplitudes, because they're just classical numbers. They commute. We don't know that they commute. In fact, they don't commute in quantum mechanics. So I have to make arbitrary choices about which way round to write the operators, which order they should go. So what does that mean? Well, the thing you have to do is make a choice, and it's convenient to write the annihilation operators to the left, to the right, since if this ever acts on a vacuum state, it sends it to 0, so that's convenient mathematically. But I realize physically I might be wrong in that choice. A different order would have made a difference, so we add in a constant to the expression, an unknown constant that we want to find out what it is. I know that's okay, because if I got the ordering wrong, I'd just have to unorder some of them. Right? I'd have to flip them from A dagger or alpha dagger, alpha to alpha dagger. But you saw the commutation relations before. Their commutation relation is just 1. So all I'm ever going to do from doing that is pick up a constant. So there's going to be a constant in here. And this is the bit where I do want to refer to my note to make sure. So, if you look at the commutation relation, the alphas don't exactly obey the thing that I said with, it's not exactly the case that alpha dagger is 1. There's a factor of n in there as well. So I have to rescale these to the a's, and we pick up this n term here. These are the real, so these are just related by a factor, by a 1 over square root to the alphas. But these are the ones, these a's then actually obey the correct simple harmonic oscillator commutation relations. They're the raising and lowering operators that we want. So we'll write it this way. So that. One other thing I'm going to have to sort of pull out of the hat here. So we have, what are we expanding? We're expanding these d plus 1 x mu fields. This mu ranges over from 0 to d. So there's d plus 1 of these, and each one has its own modes. So there are, in the first place, d plus 1 of these alphas, and this dot is a space-time, a d plus 1 space-time inner product between them. I sort of dropped the indices here. So it looks like we should have d plus 1 different vibrations in different vibrations in d plus 1 different directions that we're interested in. That's not quite right when we go to the quantum system. The ones in the time direction, the mu equals 0 ones, turn out to be unphysical. Not too surprisingly, it's anyway. And it also turns out that one of the spatial ones is dependent on the others. So really, I only am actually performing that there's actually only d plus 1, d minus 1. That are really physical. So it takes a little bit of work to see that. But it looks like there should be d plus 1 of these, one for each time, for each spatial direction plus the time one, but 2 of those turn out not to be physical or not to be independent. So really I only have to look, this dot product only has d minus 1 modes in it. Okay. So, we want to consider the first excited states of the string. So 0, it's just sitting there, well, contracted to a point, as I said. Yeah?
So I took it when we start off with d plus 1 dimensions as our space-time, that one of these dimensions is described by your tau in the string. Why do we have d plus 1 modes? Is there an extra mode in the time dimension as well? No, right there.
So for each point, I have to say how this to give it for each point, you have to say it's you have to give this d plus 1 coordinates in space-time for it. Right? I mean, otherwise I haven't told you where it is in space and time. So you can pick coordinates in which this is equal to t, say, or this is equal to x, but we're not assuming that. So in general, right.
So also for the oscillations of the string in the time coordinate, there would be a parameter like tau that would describe
that. Well, that would be in in the alpha
yes.
with mu equal to 0 term earlier on. Yeah. But it turns out the time ones lead to negative probabilities, so that's you have to take care of that. That's where we get down to d1, d minus 1. Let's see. So the first the lowest state, right? None of the modes are excited. The first excited state, you take the vacuum, so that means all of the m's for all of the modes are 0, and there's going to be a bunch of first excited states where I excite it for any of the creation operators that I have. And what I'm saying over here is, you might have thought I had d plus 1 different creation operators, one for each direction in space-time, but for reasons I'm just pulling out of a hat again, there's only d minus 1 different directions in which you can have the excitation. So what I have here, this is a first excited state where I is one of those ones. This time I don't get to excite in, and one of the spatial ones is not dependent. I'm going to set it up, just set things up so that those are the directions in which I can excite. Okay. So there's d minus 1 different first excited states, and well, you can do the, so apply the mass operator. It's pretty nice because these, it's an a dagger a term. Those are the number operators for each of the modes. Plug it in, so I is going to be equal to some value between 2 and d. Whichever one it is, all the others terms first have an annihilation operator that acts, it's not going to, so it only excites in one of the directions. So all of these are going to register, well, they're number operators for the other directions. It's not excited in those directions, so they return a value of 0. For exactly one of these directions, it's going to see, this is going to be excited to 1, so it's going to return the first excited state. So the result is going to be this. I'm just going to pick up 1, and right. So that's the, don't worry about the 0 for a second. That's just the math for plugging into the operator here and realizing that those are number operators. It's just going to return a 1 for the direction in which it was excited. Okay. But now sort of the clever bit, go back to the point that there are d-1 different states for this in this first excited state. And you ask yourself, okay, if this looks like a particle, what kind of particle can have in a d+1 dimensional space-time, what kind of particle has d-1 different states, and it's a massless spin 1 particle. Okay? It has to be massless because of that d-1. If a particle has mass, you can think about it this way, you can boost to a frame in which it's not moving, okay? And then I can boost it to another frame where the spin is in any direction that I like. If you have d-1, so it'll be like a two-dimensional sort of, say two states for spin 1, that means that the spin is then constrained to be transverse to the motion of the particle. So the only case where you can insist that the spin is transverse in all frames is if it's a massless particle. Otherwise I could do this trick to make the spin in some other direction. So because of this theory is Lorentz invariant, because of the relativistic nature of the theory, this must be a spin 1 massless particle. That's pretty quick, but it's important to understand that it's symmetry considerations, relativity that's telling you, because of the number of states, this must be a massless spin 1 particle that has transverse polarizations. Okay, so in that sense it looks just like a photon. I would say to really be a photon you need to show that it actually has the right dynamics for a photon, that it sort of plays the right role in electromagnetism, but in terms of the states, that's what it looks like. So if it's massless, well, this is the mass operator, so we know now for the first excited state the mass must be 0. So we computed what the mass is in terms of this unknown c, but it has to be 0. So now we know that c has to be 1 because of the Lorentz invariance. It sort of insists, that tells us how to do the normal ordering up here, how to do the ordering up here. Of course, it does have the unfortunate consequence that this is the first excited state, it's massless. What about the vacuum, which has even less mass? Well, it has to have negative mass squared. It has to be a tachyon, which, I don't know, we should be friends of particles that go faster than light. There's no particular reason that that's a bad thing, but this leads to energy instability in this version of the theory. Okay. Closed strings, in the quantum case, it turns out left and right excitations have to be equal. So, okay, the first excited state, you can do either sort of left or right, and you end up with d-1 squared states. So, you get sort of an index for going left and an index for going right. This is it's for sort of the same reasons, because of left and right, I've got both I've got sort of double what happens to the open string, and again, you'll have to look to the textbook here. I got something like a photon out of the open string. From the closed string, this bunch of states decompose for similar reasons into a scalar particle, the dilaton. There's something like a magnetic field, the particle that you get there. But most interestingly, there's this spin 2 massless particle, which is the description of what you would expect of the quantum of gravity. So, got all these kind of particles, so now, okay. Okay, back to that in a second. Sorry. Oh, I don't want to see. So the point I want to make now, I've got a single string, and we've now seen, when we get to the quantum level, that we can pursue that idea about its vibrations appearing like as to be the rest mass of a particle. It appears like a particle, and the vibrations determine its rest mass. So what we've got so far is we're just imagining a single quantum string. So really all we can have got out of the story so far is, to use my earlier terminology, a stringy quantum particle. We do have sort of principle of superposition, but what does it mean to have, say, a superposition of the first excited state and the second excited state on the string? Does that correspond to two particles? One of the first, the lowest rest mass, and then one of the next possible rest mass? No, I've only got one string. So basically, what I have is a superposition of two different kinds of particle. I don't have multiple strings. So, okay. So far, all I have is stringy particles, stringy quantum particles. I can understand what a quantum particle is in string theoretic terms. What we want is to understand what a quantum field theory is in stringy terms, and that's going to require many strings. Say, if I want to build a field of these photons, I'm going to need a bunch of strings that are all vibrating like photons, so they can actually have quanta. Okay, but the quanta get annihilated and created, so really I'm going to have a picture of strings where it's possible to annihilate and create strings and have superpositions of different numbers of strings. And, well, there are theories like that for the open string, but that's sort of the theory whose exact nature is not known in string theory. That's the so I want to mention that, because there's going to be, as we go on, sort of an assumption that it does make sense to have many strings and have them interacting, but that's, as it were, what's known about that is the bit that's put into, I would say, put into string theory by hand. I'm getting a little alarmed by Nick's face over here. We'll talk about this later. Okay. But, I mean, I draw this sort of picture, you kind of, here's a picture of a single string splitting into two strings, there being a kind of interaction. Now so go from one to there being two. But I haven't given you anything here to let that sort of happen other than just sort of specify. So you could specify by hand how that's to happen. What one really wants is a theory that underlies such processes. Okay. Two. Okay. Sorry. So, what we would like is to understand what happens to a string when there's a curved background. Some more general background. And perhaps what if there were other kind of classical fields around? What then would happen to the string? And more generally, how should we understand such fields? If string theory is supposed to be a theory of everything, and one starts to ask, well, what would happen if there was a curved space-time geometry that the string was living in, or there was a field of the stringy photons, or a string field of in one of the other kinds of stringy particles. What does that really mean to sort of insert the background fields? Okay. So the story we want to tell here has, in the rest of what I'm going to say, 3 parts. So first of all, we're going to focus on the gravitational field. It applies to other kinds of fields as well. So the stringy graviton particles we just discovered should be thought of, as I said, as in fact quanta of a quantum gravitational field. So ultimately then built out of strings. When you ask what happens to a string in a curved background, you put in a classical curved background, you should think of that as the classical limit of a quantum field, a quantum graviton field. So ultimately, a classical field, the classical field, right, is classical limit of a quantum field of gravitons, but those gravitons themselves are stringy. So ultimately, the classical field comes out to be stringy. Further, we're going to see, if I talk a little faster, that those classical fields, thought of that way, have to satisfy the Einstein field equations, getting us to general relativity out of string theory. So the first step is essentially going to be seeing that space-time geometry can be understood as a state of strings in a certain way, and then secondly, that space-time geometry is forced by string theory to satisfy general relativity. Okay. So, I'm afraid while Dave was giving his talk, I realized I had too much, so I was cutting some slides out, but I may not have cut enough out. So I'm going to say a few things. They may not all be essential, but I couldn't in the time figure out exactly what wasn't. In classical mechanics, Hamilton's principle is the foundation. In quantum mechanics, Feynman's principle is the foundation. Okay? Both make use of the action. Feynman's principle says the transition amplitude between initial and final configurations is the sum or path integral of e to the I of the action for every trajectory connecting initial and final states. Okay, so for particles, 2 positions, you want to know the probability of going from here to here. You think about every particle, every trajectory that connects them, calculate the action for that, and then take the exponent, sum all those up, and that gives you the amplitude from going one to the other. For a field, you think about the field configuration, pick a frame, think about the field configuration at a particular time, think about the field configuration at a later time, you want to know the transition amplitude between those two, you think about every way the field could have evolved in between those two. Okay, it's important to note that it's every particle, every trajectory. So I put every trajectory. People often say possible, but what's possible is exactly the kind of the work here. Of course, it's not just the classical ones, the one that Hamilton's principle gives you. It's not even ones that satisfy the constraints of relativity. It's not even the ones that are continuous. It's a huge class of very weird trajectories that you're talking about adding up here. Okay. So there's a lot to add up here. Maybe I should say here, of course, the space of these paths is in fact sort of a continuous one. So as we'll see in a minute, it's called this is a sum of amplitudes, but in fact you're going to have to integrate over all the space of all the possible trajectories, because they're not a countable set of things that you can add up. It's going to be a path integral equivalently. Okay, so obviously for strings I'm going to tell you how it's sitting at one time and how it's sitting at another time, and I want to know that I want the amplitude from going from here now to here now, or something like that. We'll write a prescription to that. So actually do quantum mechanics for the string and to actually apply this, it's better to switch to a different action, the Polyakov or sigma action. And the classical limit, in the classical situation, this is provably equivalent to the Nambu-Goto action. Like this morning I realized I'd only seen this equivalence in the case of flat spacetime, and I'm not sure if it holds generally, but so this is classically equivalent, but it's not, I don't think it's not clear that there's any quantum theory really for this prescription for the Nambu-Goto action. So, but if we were going back to the very first part of the talk, this would work just as well as the Nambu-Goto action that we talked about, and it looks like this. So if you have, plug in the Minkowski metric for G mu nu, this is just the same as the Nambu-Goto. You can just show that they're equivalent. But it's more useful, it's useful for, we're going to consider it in a more general background metrics. And the first step is just to split it into a Minkowski part and then whatever is left. Just a trivial kind of algebraic operation there. So, of course, the real value of the path integral method is that it lends itself to perturbative techniques, to Feynman diagrams. So, you've probably seen these in the Feynman diagrams. The lines are, the general method gives you an algorithm for generating diagrams, every kind of diagram you can think of, and then rules for assigning values to the different diagrams. In those, lines are associated with momentum integrals. You can think of those as sort of free quanta trajectories. Nodes look like interaction points, and they get associated with an interaction strength. And they appear as factors in the quantities associated with them, so you can see what's going to happen. If the interaction strength is small, then more complicated diagrams with more nodes have more factors of the coupling, right? And so, because the lambda is small, these terms are going to get smaller, and the idea is you can now have a way of approximating the path integral you're interested in computing. But I want to emphasize, this is not the sum of the paths. Okay, this is a scheme for approximating the sum of paths. These are not paths, right? The path, if you're thinking this is for a field, a path for a field is some classical evolution of the field from one classical state to another state, not anything like this. These aren't, there's two different kinds of sums. There's the Feynman path integral sum, and then there is the sort of sum of Feynman diagrams, which enables you to come up with a useful approximation to the path integral. Okay, so these are, it's worth noting these are two different things. That's your free bonus quantum field theory part of the lecture. Okay, but these ideas, this was what I'm saying, yeah. But we take the world sheet point of view. We've got fields living on a string world sheet, and they've been quantized as a quantum field. The techniques of Feynman diagrams of approximating the path integral apply to the string, and so these very ideas of path integrals and approximating path integrals with Feynman diagrams applies to calculating the path integral for a string to go from one state to another state. These techniques apply, but just bear in mind it's this particular kind of system where the space-time is two-dimensional and then you have these d+1 fields living on it. But you can apply the techniques of Feynman diagrams. It's a little bit of a strange kind of theory, because when you look at the action, you see this G mu nu here, or better maybe the H mu nu, that's what's playing, looks like it's playing the role of a coupling. So it's not a constant as I sort of assumed in these pictures. So it's a more complicated kind of system, but very intuitively, although if you look at Green, Schwartz, and Witten's book, it's a pretty intuitive argument that they give. What should be the expansion parameter that we want? Well, it looks from this, the more the curvature, the stronger this interaction is. So a natural, simple way of thinking about it is, a nice dimensionless quantity to be thinking about is what we care about. There's got to be some fundamental length scale in the string theory, which is this L sub s, the string length. And what we want is for that to be much smaller than the radius of curvature. So you can kind of quantify the amount of curvature by thinking about the radius of curvature. So from a spatial point of view, if you've got a curved space-time, you think about the smallest and largest circles you can draw that have the same curvature at that point, and then the radius tells you the radius of curvature. So the bigger the radius, right, the less the curvature, the smaller the radius of curvature, the more the curvature. So what needs to be, the expansion parameter is going to be something like, right, has to be sort of 1 over the radius of curvature. So we get a better approximation, right, the larger the radius of curvature, the less the curvature. But we'd like it to be in some, to make it dimensionless, really it's units of some fundamental string scale, like the LS. Okay. So that's important because it tells you the range of validity of what I'm about to say, and that is that the radius of curvature be large compared to the string scale. The string scale is typically set to something a couple of orders of magnitude bigger than the Planck length. So these results, so the Feynman perturbative scheme for the string is going to work as long as the space-time background curvature is large, say compared to the radius of curvature of the background space-time is large compared to the Planck length, which is kind of where you expect not to see any kind of quantum, real kind of quantum effects. If you go smaller than that, of course you're going to expect to see quantum effects. For historical reasons, the expansions are usually given in terms of this alpha prime, the Ricci slope, which is equal to the square of the string length. I realize what I also haven't explained is these quantities are also related to the string tension. So it sort of looks like there's two parameters in the theory, the T and then this string length, but these are actually related. So there's really, it all comes down to one parameter that we have here. Okay. I think a point that's sort of outside the main flow of what I'm going to say, but is really important to mention here is this now gives some empirical significance to string theory, and in particular gives empirical meaning to this G mu nu term that appears in the action. Namely, string theory in the first place is capable of producing scattering amplitudes. Think about, for another picture, what's the probability of a string in some particular stringy particle state coming in to split and go out into two different two other stringy particles. Things like that can be calculated. So scattering amplitudes calculate the amplitude for such a process to happen, and the outgoing particles to go in in the different directions, and that's something observable. That gives empirical content, and because the G mu nu appears in the action, it washes out through all of this process. It's going to give the amplitude that you calculate is going to be dependent on G mu nu on the metric. So. as I said, we actually haven't considered how a split like this would happen in the theory. But one could put them in by hand. And this is sort of what is done in string theory. Just postulate, not from first principles, but postulate that to do a full Feynman diagram for for any kind of process, I have to consider every way strings could split and join between the initial and final states. Simply postulate that there's not only do I have to do a Feynman series, a Feynman perturbation series for each particular world sheet that I have, but also sum over all the different world sheets that connect some initial state of strings to some final state of strings. So that has to be sort of done as well. So there's a sort of two-dimensional perturbation sum. For each given string, a perturbation sum for the x mu news, something like how it's embedded in space-time, but also this way, for every possible way strings can join and split, given initial and final states. And for the vertical one, there's going to be some interaction strength associated with each joining or splitting. You might think that's another parameter, but it turns out that's dynamically fixed by the theory as well. Yeah.
Nick, why did you say you put this in by hand? So you introduce a Dillon field, and then you get the string coupling, and then you just integrate over all the different topologies. What sense does it put in by hand?
So this goes back to what I was sort of saying before about it creating and annihilating strings. There really isn't a theory. I mean, okay, there's a partial theory of creating and annihilating strings, but what you would really want is to start with that and sort of apply Feynman perturbative techniques and see what the actual diagrams were from that more fundamental theory. What we have is the diagrams, but not the...
So rather than just putting the Dillon field into the action and then things come.
Yeah. It's not so much that I'm worried about the dilettante, it's just you just specify that you're going to sum over all these world sheets. But what one would like was the underlying theory that when you apply perturbative techniques to it, it said, yeah, you should sum over all these world sheets. Otherwise, right, so here's the point.
Yeah.
If this is all you have a fundamentally perturbative theory,
Yes.
and you don't know what the exact theory is that it's coming from.
Yes.
That's exactly because there isn't a theory. We're talking about creating and annihilating strings as some kind of controlled meaning. Okay. So I'm gonna skip this one so that I can actually get to the end. So what I just skipped past is all right. I think maybe I'll show you the. Sorry. You're allowed to look at the first line, but not the rest. Okay, so we're going to apply Feynman's principle to the Polyakov action. If you remember, I wrote it down with the action. I split G mu nu up into an eta mu nu plus an H mu nu part. When we exponentiate it, then I can just treat that as two different factors. Back to the previous one. Instead of a sum of this plus this, I'm going to just treat it as two factors. So that's the bit that sort of is coming from Minkowski space. There's then a nice analysis that you can do on this. You wonder, what's the significance? So this is what I would have if the space-term was Minkowski. What then should the significance of this other term be? So, well, it would take at least 20 minutes to sort of talk through it in any meaningful way. To give you the argument, I'm afraid, but it turns out that the presence of this term can be understood in terms of the presence of a background, not of a classical field that h mu nu is representing, but of a particular multi-string state. So again, I'm assuming you can create and annihilate strings. One has what's called a this corresponds, and you can sort of see why this plays out formally. Writing a term like this is exactly equivalent to writing to assuming a background coherent state of strings, a particular state of strings in graviton, each one all of them in a graviton internal state. Basically a state of 0 strings plus 1 string plus 2 strings plus 3 strings. That's what a coherent state looks like. The important thing about coherent states is they are the most classical of the quantum field states, and if you want to understand the apparent existence, the effective existence of classical fields, you understand them in terms of coherent states or near coherent states. And so this h mu nu, which looked like some classical contribution to the geometry, it was just kind of written in by hand, turns out has an equivalent description as a particular background string state. So I don't have to go outside of strings to understand what h mu nu is. It's not just some background that happens to be there. It's to be understood as the presence of other strings. So I've got some string that's scattering in some particular way, but it's doing it while interacting with a sort of sea of strings in the background. That's how this sort of should be understood. But again, for that to be possible, you have to sort of understand in some sense how strings can be annihilated and created, so that I can have a sort of a state of strings that looks like a quantum field. Okay, so that's sort of the upshot here. The same. Okay. So shut your eyes for a minute. Okay. So I have my summary kind of picture of this. We can go sort of both ways here. So imagine we have a string, the story we've had so far, each of those strings corresponds to a quantum particle. If I'm allowed to have quantum field-like states of strings, then I can have those stringy particles, a stringy quanta, and I can build up quantum field states from those stringy quanta. If they're in coherent states, and I'm thinking about the classical limit, then I get a classical field description out of that. Or going the other way, I've got a string propagating in a classical background. Well, I think I look a bit closer, I see that classical background really corresponds to a coherent state of a quantum field. That's my picture of quanta. Okay. But I now look at each of those quanta more carefully, I see it's really a string. So the picture has not just put classical fields in, it's really put in particular string backgrounds that have a classical description that have a classical description in the action if I want to understand their effect. So I was generally talking about gravitons here, but the same analysis applies to any classical field that you want. Okay. Blah, blah. All right, so I could have a scalar field. You'd add a different term to the action. If you wanted there to be a background scalar field, you'd add a term like this to the action, and that would turn out to be another kind of coherent state of strings. All right, I've made this point about single strings, so we need an unknown theory of string creation and annihilation. So here's, well, some of you may think this is the most interesting thing that's going to come up in this lecture, but we're not going to talk about it. You might say, hey, hold on. When you did this analysis, and I hope it was clear from the equation before, I split G up into an eta term and an H term, and I told you the H term was built of strings, but I didn't tell you anything about the eta term. That still seems to be in there. So how much space, is there a background space-time for strings? Is it just the Minkowski one? Okay, there's things to be sort of said there. And some things that I don't quite well, I'd like to understand a bit better. One point is, in some sense, splitting G up into these two parts is arbitrary. So it's not as if you have to assume Minkowski spacetime. And Lubo's model has an argument like that. But the analysis, I don't quite understand how to think through the analysis, because if you don't pick Minkowski spacetime, it's not certain that you're going to have gravitons that you can build things up out of. Okay. So I think that's sort of very interesting, really important for understanding geometry and string theory. Okay. So I was supposed to finish at 1:45, but we started a bit late. But I still want to try and finish pretty early, so I'll try not to go to 1. 1:30, the food's, it's not far to go. So that's the story. So what I've given you so far is a story about how to understand geometry in string theory in terms of a background of strings. That's not quite to understand gravity, because you also need that, I would say, for those stringy spin 2 massless particles, stringy particles, to really be gravitons. It's not enough that they just have that property of being massless spin 2 particles. It's not enough that they can constitute a space-time geometry. They have to also satisfy the Einstein field equations or something like that. And, well, a miracle is that, in fact, they do. Maybe it's not a miracle. I think that's also interesting. So, again, I'm going to go a bit quickly here. So suppose you have a classical symmetry, something that leaves the action S unchanged. It's an important point. Oh, by the way, philosophers of physics have been depressingly negligent in studying coherent states. So Joshua Rosala has a nice dissertation where he talks about classical limits of fields, but there's really too little about classical limits of fields that philosophers of physics have thought about. Another important topic that's like crucial to 20th century physics that's been neglected by philosophers of physics, I would say, to a large extent, is the importance of the understanding of anomalies, and the importance of anomalies in quantum field theory as a constraint. And so I'm also resentful about this negligence, because it meant I spent a lot of my time trying to figure it out when somebody could have written a paper like 20 years ago or 10 years ago, and I could have just read it. Okay. All right, as I said, it's not really a sum over paths. It really has to be an integral over paths. Okay, this was just thinking about how you would take the limit to go to an integral. But you have the Feynman e to the is, gamma is some particular path, but to go to the integral, you're going to have to be integrating over the space of paths as well, so there's going to be a measure in there as well. And as soon as you see that's really what the sum over paths is, you can see right away that just because I have a classical symmetry, it's not going to guarantee that I have a quantum symmetry. The symmetry is going to leave S unchanged, but you're going to have to check by hand that it leaves the measure unchanged. Otherwise, this integral may not have the same value. There's a further question about whether the classical symmetry is also a symmetry of the measure. Usually it is, but sometimes it's not. And then we have a quantum anomaly, a symmetry at the classical level but not at the quantum level. Could be good. It allows the pion to decay. But for local gauge theories, quantum field theory law is it leads to a failure of unitarity, and so an inconsistency in the theory. So anomalies have to be avoided for local gauge theories. It's very important in the standard model, and it's utterly central to string theory. Okay, so now we know about anomalies. What are in fact the classical symmetries of the string? So there's going to be differomorphism invariances for the x's and the sigma taus. Of course, there's space-time Lorentz transformations for flat space-time. Locally, I guess in the curved space-time. But critically, there's also a worldsheet Weyl transformation, which is if you know what Weyl symmetry is, maybe there's no point in telling you again. But I think there's a nice kind of intuitive way of thinking about what this means that also connects it sort of nicely to some philosophical thinking about identity, which is something I like. You can just think about it this way. So going back to Nambu-Goto action, the action only depends on the string area. So it's not surprising you can sort of just keep the area fixed and hold on to any point that you like on the world sheet and move it over here or move it up here without changing the area. Just imagine it as a rubber sheet. You don't change the action. Well, the symmetry way of thinking is that that really wasn't any change at all in the first place. So you can do that. The Weyl symmetry preserves the causal structure. So as long as you keep time-like points time-like and so on, I can move things around, and there can't be any fact about which one at one time is the one at another. And even at a particular time, we have tension, it's a constant tension. I really need a third hand. Okay, can you just move a bit to the left or the right? And then it drops back, right? For a string, for a regular spring, there actually is an equilibrium state where the thing, for a Hooke's law spring, where everything is stretched evenly along it, and if you differentially stretch in the middle, it'll pop back to where it is. But that's because, right, Hooke's law, the tension will be greater in some places to the other, so there's an equilibrium state. So you can, because of Hooke's law, there is a way of sort of distinguishing these different states of the string, whether this part is moved over here or not. The tension is constant in the string, so there's nothing like that. You can sort of stretch bits across, and it's just the same. There's no difference. Okay, so there's a sort of failure of identity for the parts of the string that you don't have for the sort of spring Hooke's law. Okay. So I think that's a nice way to sort of think about it. One could be a bit more careful and kind of talk about this in terms of other symmetries, but I think that kind of gets you the flavor. As you know, Weyl symmetry, it's avoiding the anomaly that leads you to 26 dimensions. If you don't have supersymmetry, or 10 dimensions, if you do have, I think it should be 25. Sorry, that's the d plus 1, right? Not the d. But crucially for our point, demonstrably, demanding the Weyl symmetry remains in the quantum theory requires at lowest order, which means in alpha prime, so in the sort of string length squared, that the background fields satisfy the appropriate Einstein field equation. So in the case that we wrote up, where you just have G mu nu as the background field, the system is required to have Ricci flatness. If there are other kinds of matter fields around, they're going to have to satisfy the Einstein field equations. Okay? Lowest order, right? And remember that what actually comes out of the theory is an expansion in alpha prime. So there will be quantum corrections coming out of this to the Einstein field equations, but to lowest order in alpha prime, you get the Einstein field equations out. But I want to, again, stress, you shouldn't think of this as a sort of constraint on the classical backgrounds that you can sort of dump a string into, right? Because we saw the classical backgrounds are themselves string states.